Here's a video on how to do the MIS or MOS diode or capacitor experiment. So you'll see this tutorial, you'll have access to it. The important thing is the sample file is there already for you. This is a previous experiment. But here are the dimensions. And just something I want to point out is that W sub is the width of the substrate, but this gate contact and body contact are dimensionless. It covers the whole width of the substrate, but there's no dimension to it. Then we have the oxide layer, and that is in microns. So 0.02 microns would be 200 angstroms. All right. And then here we have the substrate, but I've broken it into two. They're both silicon, they're both doped the same, but I add an area that will have a tighter mesh because I'll take the substrate doping and calculate the depletion layer max, right? Because that's where the action will happen. And then I add a thickness of the substrate on top of that, so that it'll it'll simulate possible no matter what we're doing. So if we look here in the code, all right, there's our NI, all the variables, and here's me calculating the depletion width max. All right. So it'll draw a rectangle of that, and then it also that grid will be tighter later on. And the simulation's slightly different in that we have to set up a device, a system, where we read in the file, but then we're putting it into kind of a SPICE simulator. I'm still doing regular TCAD simulation, but now we are changing the voltage from 20 to -20, so we're going from inversion to accumulation for p-type, which is what you're supposed to do. But we have an AC simulation. And so if I double click here, AC Centaurus device. So you have the gate, and then C gate to gate, and there's our CV curve. And it pulls off C minimum, pulls off C max, takes care of it automatically calculates the area for you. All right. So that if you look at the inspect script, it reads in the TOX that we set prior, converts it to centimeters, and then goes through that whole extraction routine to find everything. Now, yeah, it's even got the, I believe, if you double click the inspect script, right, it gives you everything that it used to calculate. All right. But it just put these various things in your file. Now, yep, the extracted substrate doping is close to the substrate doping, right? But it's not always the same, right? And the fixed oxide charge can sometimes go negative, and that is really based on how trying to extract things at high frequency can be difficult. That really knowing the true C min is difficult, but it is a really good screening tool. All right. In the homework, you'll be asked to just, you know, edit that to 5e to the 10, and you can rerun it. You don't need to play with the number of grids that's set for you. Everything should work. Really, you just control these two things, right? And one, you're going to use your hand calculations and 1e to the 16 substrate doping and come up with a TOX to create a threshold voltage, right? Then you'll verify it. But then you might have to adjust your TOX here to get within 5%. Then the other one is you're given a TOX and you have to calculate your NA, right? And then you have to verify it in simulation. So let's just scroll down. Now, instead of minus, no, that's not right. You know, it will be a little bit different. Just use the regular aluminum. Should just get rid of that. Just use the regular aluminum. You might get a slightly different answers because the simulator's set up for a mercury probe, but that's okay. So again, fixed oxide charge 5 times 10 to the 10th. First one designed to a threshold voltage of 0.5, but I give you the substrate doping and I give you the semiconductor, so find TOX. Exercise 2, it's the opposite. And that's that. Report should have all major sections. It's just, you know, abstract theory, introduction, but you know, really no more than 2 pages, and we'll leave it at that. Just don't throw a bunch of screen grabs with no context. So I'll just save this as a PDF. Well, I'll save it later. I gotta redo some of the figures, the table of contents. But that's pretty much it.